Hello everyone, we're going to take a look at 3 example problems of finding a tangent line approximation of a function, also known as linearization. As we walk through these, keep in mind at the heart of it what you're doing. All you're doing is finding the equation of a tangent line. That's it. What often throws students off about this is the model we use. The model is really just a variation on point-slope form of a line. It states that the linearization that we're seeking, L of x, is going to be equal to f of a, so that's the y value. In this case, for this problem, the 0 is our a value, plus f prime of a. Now think about what that is. That's really just the derivative, the slope of the tangent line, times x minus a. And compare that to point-slope form of a line. Really all it is y equals y1 plus m times x minus x of 1. That's really all it is. So it's simply a variation on point-slope form of a line. So keep that in mind as we do this. There's a couple things that we're going to need. We know what a is at this point. It's the point 0. We're trying to find the tangent line approximation for 1 plus sine of x at the point 0, 1. So we know a. We need to find f prime of a and f of a. So let's do each of those first. Well, 1 is simply f of a. So we have that finished. That's easy. We need to find the derivative. I'm going to go ahead and do this over to the side here. Derivative, of course, is simply cosine of x. And we need to find f prime at a, so f prime of 0. That's simply going to be 1 cosine of 0. That's all we really need to substitute into our model. So we have L of x is equal to f of 0, so that remember that was 1, plus, now our derivative was also 1 by chance, times the quantity x minus 0. We can simplify that nicely, and we have a final linearization of L of x is equal to 1 plus x. Now think about what that means and the whole idea behind linearization. Let's take a look at the graph of 1 plus sine of x you see here in blue, and I've gone ahead and already drawn in that tangent line we've gotten, 1 plus x. And you can see, if you think of just how you graph a linear equation, I did my best. It goes through 1 on the y-axis, and it pretty much looks like it has a slope of 1 about. Now think about what this tells us. For x values near 0, here's 0, the function 1 plus sine of x is very well approximated by the linear equation y equals 1 plus x. If you take a look at the graph for values of x, very, very, very close to 0. Notice how when you're looking at the curve right here, there's almost no difference between where the linear equation sits and the curve itself sits. They almost become indistinguishable. That's the idea. But notice as you get farther and farther and farther away from 0, maybe if we looked at an x value all the way over here, a little past pi over 2, if we trace that up, obviously that's hitting the curve right here, but it's hitting the tangent line all the way up here. Notice how there's that big difference? So that's what we're talking about, is how the function values, the 1 plus sine of x function values themselves, can be very well approximated by the simple linear equation 1 plus x for values very, very, very close to 0. The farther you get from 0 in terms of an x value, that approximation is not as good. Think of the delta neighborhoods you learned with the formal definition of a limit. That's really where all that comes back in here. So let's take a look at another example. We are now finding the linearization of f of x equals 1 over x at a equals 1. So let's go ahead and set up our model so we remember what that is. L of x is going to be equal to f of a plus f prime of a, that's our slope that we need, times the quantity x minus a. So a is 1, obviously. We can do f of a, f of 1, that's simply going to be 1. Let's go ahead and do our derivative. Our derivative is going to be negative 1 over x squared. You can think of the original function as x to the negative 1 and do the power rule from there. So f prime of 1, our a value, is simply going to be negative 1. So that's our slope that we're going to use. Now we can simply substitute everything in. So we have our linearization. F of 1 was 1, plus our slope in this case was a negative 1. We have x minus 1. We can go ahead and simplify that a little bit. And we have a linearization of negative x, negative 1x if you prefer, plus 2. Again, if you think about what that means, if we were to draw the curve 1 over x, draw the tangent line negative x plus 2 for values of x very close to that x value of 1, our a value, the difference is going to be incredibly small between the actual function value, the 1 over x function value at that x value, and the value given to us by substituting into negative x plus 2. Another thing to think about, because I mentioned earlier all you're really doing is writing the equation of the tangent line. This would have been the same answer you would have obtained if I had asked you to find the equation of the tangent line to 1 over x at x equals 1. It's the exact same answer. It's really just a different interpretation, a different question. Let's take a look at one last problem. Here we are asked to find the tangent line approximation at the point 2, 3 of the function f of x equals 1 plus x cubed. We then want to use that linearization we obtain to estimate the function value at 2.01. So our a value at this point is 2 from the point 2, 3, and notice how the function value we're seeking is just a little bit bigger than 2. Remember what we were talking about in that first example with the graph of the 1 plus sine of x equation. So we're always talking values very close to our a value within a very small delta neighborhood. Let's go ahead and just start out our linearization like we have been. So we know a is 2. We need to know f of 2. That's simply given to us in the point itself, so that's 3. We need to find our derivative. This will require us to use the chain rule. We'd have 1/2 1 plus x cubed to the negative 1/2. Then we need to multiply that by 3x squared. Let's simplify it a little bit. And we have 3x squared over 2 square root of 1 plus x cubed. We need to find f prime of 2. You should get 12 over 6, which of course simplifies to 2. Now we can substitute everything in. F of a was 3. Our slope that we obtained from our derivative was 2. And we have times the quantity x minus 2. We can go ahead and simplify it a little bit. We have 2x minus 1. And that is our linearization. We want to use that to estimate the actual function value at 2.01. Where this really used to have benefit was back in the old days before we had calculators to do this for us, and we had to do everything by hand. Because if I needed to substitute 2.01 into square root of 1 plus x cubed and do all that number crunching by hand, it would not be fun. It's a lot easier to simply substitute 2.01 into 2x minus 1. Now you do have to be careful how you write this out. We are seeking the function value at 2.01. Remember, that is only going to be approximated by the linearization equation. So using an approximately equal to symbol, either the equal to with the dot over it or the two little squigglies, is a necessity. So remember, it gets substituted into 2x minus 1. So we have 2 times 2.01 minus 1. All right, this is coming from our 2x minus 1 that we had for our linearization equation. Well, that's pretty easy to do by hand, and just do in your head, you get 3.02. So that is our estimation using linearization of the true function value at 2.01. Now, just for kicks, try this in your calculator. Go ahead and do in your calculator square root of 1 plus 2.01 cubed. Go ahead and try that in your calculator. See what you really get. You get I have it out to a few decimal places, 0.02003. See how close that is to what we obtained through the linearization? That's the idea behind all this. So it's kind of cool to see how you can actually get a complicated function value, square root of 1 plus 2.01 cubed. You can get something pretty close from a simple linear equation. And that's the idea behind tangent line approximations and linearization.